Hello, welcome to Rolls Battery Engineering's webinar series. Today we're going to talk about series parallel connections for battery banks, what to do and what not to do. This is a webinar, so some housekeeping issues. We try to keep these to 30-40 minutes. This one will probably be closer to about 30 minutes. Everybody's microphone is muted, so we can try to eliminate background noise, echoes, all that wonderful stuff. During the webinar, there is a chat pane. If you want to ask questions, go ahead and enter your message in the chat pane, and you can post it to everybody. You can post it directly to me, whoever you want to post it to. We'll be sure to address those questions either at the end or while we're discussing. This is going to be posted on YouTube. If you're listening or watching this on YouTube, please feel free. There's a comment section below the video. If you have any questions, concerns, comments, anything, feel free to post them there. If you don't want to post them there, if you send me an email at steve@strut.com, I'll be more than happy to help you out there. Okay. All right. So here's my contact information. Again, steve@strut.com is my contact information, my toll-free number, and of course my cell phone number. I do spend a couple hundred days a year on the road traveling, doing training at events all over the world, really. So if I'm away, it'll say I'm away. Please give me some time to respond. All right, so talk about batteries. Batteries, when you're building a battery bank, a couple things to remember. First and foremost, series circuits, you add voltage. So if I took two 6-volt batteries and put them in series, say they were 6-volt 100 amp hour batteries, I'm going to get a 12-volt 100 amp hour battery. Okay. If I take those two 6-volt batteries and put them in parallel to each other, I'm going to get a 6-volt 200 amp hour battery. So voltage adds in series while current adds in parallel. Something to definitely keep in mind to what you're doing. As for battery capacities, lead acid batteries in general, most lead acid batteries are manufactured in 2-volt blocks, 2-volt cells. There are mono blocks in 4-volt, 6-volt, 8-volt, and 12-volt mono blocks. To make a 12-volt, 24-volt, 32, 36, 48, or all the way up to I've seen as high as some of 900,000 volt DC systems out there. To make those, you have to run batteries in series to make that to happen. To get your kilowatt hours, your kilowatt hours of storage, that's where you need to combine either 1, 2, or 3 parallel strings to be able to get that. Try to avoid more than 3 parallel strings. The reason you want to avoid more than 3 parallel strings is that causes imbalances, for one. 2, at a 48-volt system, you're going to have 24 cells to maintain on a single series string. That goes to 48 for 2 strings, 72 for 3 strings, 96 for 4 strings, 120 for 5 strings. If you've got 120, 160 cells to maintain, your customer's never going to maintain them. You can see pretty large imbalanced loads or problems with the loads by running more parallel strings. A lot of customers will call me up and say, Steve, what kind of voltage system do I need? And that really varies on the user. It really varies on the installer. It varies on the size of the system that you're putting in. Back in the 70s and the 80s and some of the 90s, 12-volt systems for solar were pretty common because we didn't have MPPT controllers then. Well, we had with pulse width modulation controllers. Panels were really expensive. You only had PWM charge controllers, so you had to match your panels together. Things were a bit more. There was a bit more requirements on the components you had to use. 12-volt systems are generally in today's world, 12-volt systems generally for automotive or marine applications. Small solar systems, where you see developing countries like Africa, Latin America, where you're dealing a small school system or a small village system. You want to try to keep those as simple as possible. So lower voltage equals a higher current, which also increases the requirements for making sure your conductors are properly sized. and a 12 volt, a 3000 amp, or an inverter running at 12 volts, and it's a 3000 watt inverter, will pull 250 amps of DC current. That same inverter running at 24 volts is going to pull 125 amps of current. So right there is an efficiency gain and a huge cost of savings for cabling. 32 volt, 36 volt systems. Those are typically 32 volt systems, fishing net vessels, and most of your locomotive starting systems. 36 volt forklift applications are also locomotive starting applications. You see some places in Europe, but you also see it quite often on the East Coast United States, New England, Maine. You see it in Vancouver, BC, or BC, Northwest BC, or even Alaska and Seattle. You'll see a lot of 32 volt boat applications for fishing vessels and stuff like that. So that's where you start to see 16 and 18 cell battery banks. In today's world, most of the systems, when you start getting above that 3 to 12 kilowatt hour, 3 to 15 kilowatts of energy usage, you start to see 48 volt systems. Okay. And the reason for that is of course that current, that same 3000 watt system at 24 volts that was pulling 125 amps now is, 60 some odd amps. If you're running a 10 kilowatt system, 10 kilowatts at 48 volts is only about 200 amps of current. So your DC breaker buses, your DC bus has got to be rated for, 300 amps, while your cabling and fusing is all rated for, 200, 250. So you're using 4-aught cable with 250 amp breakers. Of course, the length of those cables also matters. I'm just not accounting for that. Of late, in the last 4 or 5 years, what you find is customers are wanting bigger systems. They're wanting storage systems in excess of 500, 1,000, 500 kilowatt hours, a megawatt hour of energy storage consumption. With those systems, trying to do a megawatt hour of energy storage at 48 volts, you're talking 8, 10, 12 parallel strings of 2,000, 4,000 amp hour capacity batteries. That's just not really feasible in most applications. You want to be very careful with that. Just recently, I was at a site in Utah on Lake Powell. It was 4 parallel strings of 196 2-volt cells run in series. So it was 196 batteries in series with 4 parallel strings of batteries in parallel, or 4 parallel strings of batteries. It was a fairly significant system on a 600 volt DC inverter. So something to watch out for. Here's an example of a 6-volt battery bank, or I'm sorry, a 24-volt battery bank using 6-volt batteries. So what we have here is you have we've got you've got your cells. So you've got 1 cell, 2, 3 cells. That tells me at 2 volts per cell, there's a 6-volt battery. You've got 12 cells in series. Those 12 cells give you that 24-volt battery bank. When you're looking at this, if we have 100 amps of current being drawn, we're going to have 100 amps of current here. We're going to have 100 amps of current here. We're going to have 100 amps of current here, 100 amps of current here. So your current's all going to be the same throughout the string. And so the impedance of the batteries doesn't affect the current like it would if you were doing 2 and 3 parallel strings. All right, so go on to the next slide. So on the next slide, we have 2 parallel strings. You have parallel string 1 and you have parallel string 2. We have that same 100 amps of current. Now what's going to happen is that current's going to subdivide between those parallel strings. The series cables, the series connections still don't matter, but these parallel connections are very important to make sure that they're the same size and same length, because if they're not, then what can happen is you can get an inherent voltage drop across these, or current drop across the voltage drop across these, and that'll change how much current is available to each parallel string of batteries, and that will affect your overall charging, and it'll cause charging imbalances. One of the things I want to point out here is you want to be careful of is that what I'm doing here is I have the positive connection here. I have my positive bus going down to this connection here. What I'm doing is I'm pulling these connections off the corners. I'm trying to force the current to flow as evenly as possible through the battery bank. If this tap connection was connected here instead, and what would happen is that would force most of the current through this string of batteries, because I would get a current drop across these lines, and so these batteries would charge unevenly. This is an example of a 12-volt battery bank using 2-volt strings. So I have cell 1, 2, 3, 4, 5, 6. Again, since I have one series string, my currents are all going to remain the same throughout the entire battery bank. Pretty simple, pretty easy, pretty simple, pretty easy, and it makes it easy to set up. Also makes it easier to troubleshoot. Instead of using multiple strings of batteries, what a lot of people do is they'll take a bunch of 8D batteries and run 4 or 5, 6 of them in series, or 6 of them in parallel. Now you've got 12 times 6, so you got 72 cells to worry about. Your maintenance costs also go down. This is an example of a 24-volt battery bank using 2 parallel strings. Now I'm going to show you a couple different ways to connect this, and I'm going to bring them up on this slide here. We have example number 1 and example number 2. The biggest differences between these is what I've done is I reversed the polarity on the bottom row of batteries on this string. That way, my tap-offs to go to my DC bus are at one point. So that keeps these connections, these cables, as low and as short as possible. I don't want to have big long connections here because that just increases your cost on installing or on designing these systems. Plus, the only thing you got to be careful of is when you're troubleshooting, when your techs go out or when your owner goes out, if you pull this battery out, you need to be sure that you put it back in the same way it was taken out. Otherwise, you can reverse polarize the battery, and that would cause problems down the line. You don't want to reverse polarize your battery. Not a good thing. Just give you a picture example. Basically, what you've got is we've got an Outback green metal box with looks like an FW inverter from Trace Engineering. Look at these parallel cable runs that they've got installed here. Look at the differences in the lengths. This system's been installed for quite some time. He's got huge, long parallel cable connections. I mean, this one's got to be 30 feet right here. Those connections, this is one string and this is one string. These batteries are not charging anywhere near even, and so you're running into major problems in charging there. And that's the problem with the customer, is they were seeing a huge imbalance in charging, and it was causing problems with the batteries. So one of the other things I like to do, just a helpful hint, is I like to number the cells. When you number the cells, it gives you a constant measurement of what cells you're running. Like, for example, we've got 12 cells, 12 batteries. When I'm taking my specific gravity measurements, cell number 3 always stays with cell 3. So that way I can track and have an accurate recording. The other thing that it does, a lot of people do not like taking specific gravity measurements or doing maintenance on their batteries. So one of the things you can do to help minimize the amount of time that customers spend on doing your batteries is, I will tell people, is on the odd number months, check your odd number cells. Check cell 1, 3, 5, 7, 9, and 11 on the odd number months. On the even number months, check 12, 10, 8, 6, 4, 2, and 2. If you do that, at least every couple months, you have a full reporting of all the cells in the battery bank. Battery banks batteries are like electronics. When they fail, they tend to fail over a long period of time, or the symptoms present themselves over a long period of time. Usually a 3, 4, or 6 month period of time before there's actually a failure. Now we're going to talk about some problems with parallel connections. This is an example of a 5 parallel string of 6-volt batteries. These 6-volt batteries are configured in 5 parallel strings. They are 6-volt, 420 amp hour batteries, basically our S550s. They're configured at 24 volts. So the battery bank capacity is at 2,140 amp hours. Each battery has an internal resistance of 0.0144 ohms. And each string has its own resistance or impedance of 0.00576 ohms. That's not including the cables. I want to try to keep it as simple as possible. Okay. So if I have a 100 amp current source, ballpark, what do you think that the amount of current per parallel string we're going to have here? So if we follow Ohm's law and make the calculations, it's pretty simple. We have 5 parallel strings. We have a 100 amp current source. All the resistance are the same. So we're going to get an equal distribution of current across each parallel string of batteries. Okay, and that's when the batteries are healthy. All right, so batteries are 2, 3, 4 years old. They've been maintained. They've been working. You know, let's say this battery here develops a little bit more internal resistance. So now the internal resistance in this series string goes up. When that internal resistance of that string goes up, what happens is now this battery is causing higher resistance, which is dropping the amount of current going to that string while raising the amount of current going to my other 4 strings. So now in effect what's happening is that this string of batteries isn't getting charged enough, while these 4 strings of batteries are getting overcharged. Okay, so they're actually being charged too much. And so the problems that causes, not only does it cause the voltage-based inverters to shut the charge off early because it sees the current drop off early, or it sees the voltage rise and current drop too early. But the other issue is when you shut off your charging source, what happens is now, let me clear this off. Now what happens is that this string now feeds off of the rest of the batteries. So current is now feeding in from the other 4 parallel strings into that one string. And so with flooded lead-acid batteries, it doesn't happen very often, but you see it a lot with valve-regulated lead-acid batteries where you have multiple parallel strings, is you can see what's called thermal runaway. And thermal runaway, what's happening is as these batteries are accepting current from the rest of the strings, these batteries are getting hot. The hotter they get, the lower the voltage drops. So voltage drops, and so what happens is when the voltage starts to drop, now the batteries continue to get hotter and hotter and hotter and hotter, eventually to the point where if it's a valve-regulated battery and you start seeing temperatures over 52 degrees Celsius or 125 degrees Fahrenheit, you can actually have the cases fail and they'll blow apart. So again, it's a definite another thing to try to avoid. So the economics of this whole discussion. If I go and I connect 6-volt, 420 amp hour batteries in a 24-volt battery bank, I've got 5 parallel strings of batteries. So it's a 2,140 amp hour battery. Ballpark, that's going to cost you on the street, it's going to cost you around $7,500 US. Your typical life, unless the customer put in the extra maintenance, they have to separate the strings, charge each string separately, and then put them back together and recharge them. You're going to see equalization requirements because of the imbalance of the charging. unless they put in that extra maintenance, you're probably looking at a 5 to 7 year life realistically. That same system, you can do, if you spend an extra $1,500 and you go with 2 parallel strings of S1450s, basically you're looking at 24 batteries. You're only looking at a few more cells, a few more batteries. You're going to get an 8 to 12 year lifetime because you've got two series parallel strings in this bank. And so you're able to maintain that system much cleaner than you would with a 5 parallel strings of batteries. Try to use, so just a summary, try to use as few as possible parallel strings. There are many installers out there who, have got years of experience, who won't do systems more than one or two parallel strings anymore. And the reason for that is they've learned from experience that having multiple parallel strings is usually a bad idea. The other bonus is if you're using 2-volt cells and you have a 24-volt or a 48-volt system, you can drop out a cell and continue to use the battery bank while you're waiting for the replacements. I'll show you how that works on the next slide. If you're using 6-volt batteries, and the 6-volt L16 is a very popular battery, typically my limit's about 2 strings. And the reason for that, what's nice to have that, if you do have a problem with one of the batteries, you can drop one of the strings out and still operate, and still be in operation. Generally for the amp hour capacity, about 800 amp hours is where you want to start looking at getting into a 2-volt cell instead of using 4-volt, 6-volt, or 12-volt monoblocks. And the reason for that is your costings typically, when you start looking at 2,000 amp hour battery bank, to do it with 12-volt or 6-volt batteries, well, it may be about 10% cheaper up front, but your maintenance costs go up and your replacement costs are going to go up in the long run. So that troubleshooting trick. So we have a single string of batteries. This is 48-volt system. That single string of batteries, battery 9 has an issue. So when we start to troubleshoot, we find out that this battery here is measuring, 0 volts. Instead of leaving that battery bank in the string, we can pull that battery out of the string. So what we do is disconnect it, disconnect this cable, and we connect this cable over to here. So this cable is taken out, that cable is connected over to there. Okay. And so actually I'll draw it better this way. So this cable goes right over to here. So now we have a cell with 23 cells instead of 24 cells. So this allows me I can still operate. But what I have to do is I got to reduce all my voltage-based set points by your volts per cell value. And how you figure that out is, let's say you're absorb charging at 59.6 volts. Okay. So 59.6 volts divided by 24 cells, that means we're charging at 59.6 divided by 24 volt cells. So 59.6 divided by 24, that's actually a little higher. It's about 2.45. So we'll just say it's 2.43 for just an example. So 2.43. So now we have to adjust all of our charge voltages down by that 2.43 volts per cell. This applies for bulk, float, absorb, equalize, low battery cut in, low battery cut out, generator start voltages. Anything that has a voltage-based setting, that applies. So you need to make those adjustments. If you don't, if you just leave it the way it is, now you're charging 23 cells. So you say you're charging at 59.6, 59.6 divided by 23. Now you're charging at almost you're charging at an equalization voltage. That may be okay if the batteries need to be equalized, but to leave it there permanently would be a bad idea, or at least especially if the battery is going to take a little bit to get. At this point, I answer any kind of questions that come up. I don't see any questions, so I'm going to go on to the next. Again, here's my contact information. This video is going to be posted on YouTube. If you have any questions or comments or concerns, feel free to post at the bottom of the page. I will be more than happy to accept any feedback. That way I can get better at these. Or if you want to do it privately, you can send me an email at steve@surrett.com. I'll be more than happy to answer your questions for you. Thank you very much for watching this video, and hopefully I'll have a few more to come.